Jump to content. Main menu. Main menu, move to sidebar, hide. Navigation. Main page, help browse cookbook Wikijunitor feature books recent changes random book using Wikibooks. Community. Reading room forum community portal bulletin board help out. Policies and guidelines contact us. Search. Search. Appearance. Donations create account login. Personal tools. Donations create account login. Pages for Longbout editors learn more. Contributions discussion for this IP address. Contents move to sidebar hide. Beginning. 1. Introduction. 2. Basic wave theory toggle basic wave theory subsection 2.1 plane wave pressure distribution in pipes. 3. Basic filter design toggle basic filter design subsection 3.1 low pass filter. 3.2 high pass filter. 3.3 band stop filter. 3.4 design. 4. Actual filter design toggle actual filter design subsection 4.1 absorptive. 4.1.1 examples. 4.2 reactive. 4.2.1 examples. 4.3 performance. 4.3.1 noise reduction in HAR. 4.3.2 insertion loss IL. 4.3.3 transmission loss TL. 4.3.4 examples. 5 links. 6 references. Toggle the table of contents. Acoustic/filter design and implementation. Add languages. Add links. Book discussion. English. Read edit source view history. Tools. Tools move to sidebar hide. Actions. Read edit source view history. General. What links here related changes upload file special pages permanent link page information site this page gets shortened URL download QR code. Sister projects. Wikipedia Wikiversity Wiktionary Wikiquote Wikisource Wikinews Wikivideo Commons Wikidata Media Wiki MetaWiki. Print/export. Create a collection download as PDF printable version. In other projects. Wikidata item. Appearance move to sidebar hide. From Wikibooks, open books for an open world. Acoustics. Introduction edit vertical line edit source. Acoustic filters, or mufflers, are used in a number of applications requiring the suppression or attenuation of sound. Although the idea might not be familiar to many people, acoustic mufflers make everyday life much more pleasant. Many common appliances, such as refrigerators and air conditioners, use acoustic mufflers to produce a minimal working noise. The application of acoustic mufflers is mostly directed to machine components or areas where there is a large amount of radiated sound such as high-pressure exhaust pipes, gas turbines, and rotary pumps. Although there are a number of applications for acoustic mufflers, there are really only 2 main types which are used. These are absorptive and reactive mufflers. Absorptive mufflers incorporate sound-absorbing materials to attenuate the radiated energy in gas flow. Reactive mufflers use a series of complex passages to maximize sound attenuation while meeting set specifications, such as pressure drop, volume flow, etc. Many of the more complex mufflers today incorporate both methods to optimize sound attenuation and provide realistic specifications. In order to fully understand how acoustic filters attenuate radiated sound, it is first necessary to briefly cover some basic background topics. For more information on wave theory and other material necessary to study acoustic filters, please refer to the references below. Basic wave theory edit vertical line edit source. Although not fundamentally difficult to understand, there are a number of alternate techniques used to analyze wave motion which could seem overwhelming to a novice at first. Therefore, only 1D wave motion will be analyzed to keep most of the mathematics as simple as possible. This analysis is valid, with not much error, for the majority of pipes and enclosures encountered in practice. Plane wave pressure distribution in pipes edit vertical line edit source. The most important equation used is the wave equation in 1D form. 1, 2, 3. Therefore, it is reasonable to suggest, if plane waves are propagating, that the pressure distribution in a pipe is given by P equals PIEJT, Kx plus PREJT plus Kx backslash display style backslash mathbf P equals backslash mathbf pi e circumflex accent J backslash omega t Kx plus backslash mathbf PR e circumflex accent J backslash omega t plus Kx, where pi and PR are incident and reflected wave amplitudes respectively. Also note that bold notation is used to indicate the possibility of complex terms. The first term represents a wave traveling in the plus x direction and the second term, x direction. Since acoustic filters or mufflers typically attenuate the radiated sound power as much as possible, it is logical to assume that if we can find a way to maximize the ratio between reflected and incident wave amplitude, then we will effectively attenuate the radiated noise at certain frequencies. This ratio is called the reflection coefficient and is given by R equals PR PI backslash display style backslash math BFR equals backslash left backslash frac backslash math BFPR backslash math BF pi backslash right. It is important to point out that wave reflection only occurs when the impedance of a pipe changes. It is possible to match the end impedance of a pipe with the characteristic impedance of a pipe to get no wave reflection. For more information see 1 or 2. Although the reflection coefficient isn't very useful in its current form since we want the relation describing sound power, the more useful form can be derived by recognizing that the power intensity coefficient is simply the magnitude of reflection coefficient square 1. RP equals vertical line R vertical line 2 backslash display style R underscore backslash pi equals backslash left vertical line backslash math BFR backslash right vertical line circumflex accent 2. As one would expect, the power reflection coefficient must be less than or equal to 1. Therefore, it is useful to define the transmission coefficient as Tp equals 1, Rp backslash display style T underscore backslash pi equals backslash left 1 R underscore backslash pi backslash right, which is the amount of power transmitted. This relation comes directly from conservation of energy. When talking about the performance of mufflers, typically the power transmission coefficient is specified. Basic filter design edit vertical line edit source. For simple filters, the long wavelength approximation can be made to make the analysis of the system easier. When this assumption is valid, e.g. low frequencies, the components of the system behave as lumped acoustical elements. Equations relating the various properties are easily derived under these circumstances. The following derivations assume long wavelength. Practical applications for most conditions are given later. Low-pass filter edit vertical line edit source TPI for low-pass filter. These are devices that attenuate the radiated sound power at higher frequencies. This means the power transmission coefficient is approximately 1 across the band pass at low frequencies. See figure to right. This is equivalent to an expansion in a pipe, with the volume of gas located in the expansion having an acoustic compliance. See figure to right. Continuity of acoustic impedance. See Java applet. Acoustic impedance visualization at the junction. C1 gives the power transmission coefficient of Tp11 plus S1, S2 SKL2 backslash display style T underscore backslash pi backslash approximate backslash frac 11 plus backslash left backslash display style backslash frac S underscore 1 S2 SKL backslash right circumflex accent 2. Where K is the wave number, C wave properties L and S1 backslash display style S underscore 1 R length and area of expansion respectively, and S is the area of the pipe. The cutoff frequency is given by FC equals CSPLS1, S backslash display style F underscore C equals backslash left backslash frac CS backslash pi LS underscore 1 S backslash right. High-pass filter edit vertical line edit source TPI for high-pass filter. These are devices that attenuate the radiated sound power at lower frequencies. Like before, this means the power transmission coefficient is approximately 1 across the band pass at high frequencies. See figure to right. This is equivalent to a short side branch. See figure to right with a radius and length much smaller than the wavelength lumped element assumption. This side branch acts like an acoustic mask and applies a different acoustic impedance to the system than the low-pass filter. Again, using continuity of acoustic impedance at the junction yields a power transmission coefficient of the form 1. Tp equals 11 plus P 2 to SLK2 backslash display style T underscore backslash pi equals backslash left backslash frac 11 plus backslash left backslash frac backslash pi 8 circumflex accent to SLK backslash right circumflex accent to backslash right. Where A and L are the area and effective length of the small tube, and S is the area of the pipe. The cutoff frequency is given by FC equals C2 to SL backslash display style F underscore C equals backslash left backslash frac CA circumflex accent to SL backslash right. Band stop filter. Edit vertical line. Edit source TPI for band stop filter. These are devices that attenuate the radiated sound power over a certain frequency range. See figure to right. Like before, the power transmission coefficient is approximately 1 in the band pass region. Since the band stop filter is essentially a cross between a low and high pass filter, one might expect to create one by using a combination of both techniques. This is true in that the combination of a lumped acoustic mass and compliance gives a band stop filter. This can be realized as a Helmholtz resonator. See figure to right. Again, since the impedance of the Helmholtz resonator can be easily determined, continuity of acoustic impedance at the junction can give the power transmission coefficient as 1. TP equals 1 plus C/2SL/SB. C2/V2 display style T underscore pi equals left frac 1 plus left frac C/2S omega L/S underscore BC circumflex accent to omega V right circumflex accent to right, where SB display style S underscore B is the area of the neck, L is the effective length of the neck, V is the volume of the Helmholtz resonator, and S is the area of the pipe. It is interesting to know that the power transmission coefficient is 0 when the frequency is that of the resonance frequency of the Helmholtz. This can be explained by the fact that at resonance the volume velocity in the neck is large with a phase such that all the incident wave is reflected back to the source one. The 0 power transmission coefficient location is given by FC equals C2PSBLV display style F underscore C equals left frac C to pi right SQRD left frac S underscore BLV right. This frequency value has powerful implications. If a system has the majority of noise at one frequency component, the system can be tuned using the above equation, with a Helmholtz resonator, to perfectly attenuate any transmitted power. See examples below. Helmholtz resonator as a muffler, F equals 60 Hz. Helmholtz resonator as a muffler, F equals FC. Design. Edit vertical line. Edit source. If the long wavelength assumption is valid, typically a combination of methods described above are used to design a filter. A specific design procedure is outlined for a Helmholtz resonator, and other basic filters follow a similar procedure. C1. Two main metrics need to be identified when designing a Helmholtz resonator. 3. Resonance frequency desired, FC equals C2PCOV display style F underscore C equals frac C to pi frac SQRDC underscore OV where CO equals SL display style C underscore O equals frac SL. Transmission loss, COV to S equals CO then ST display style frac SQRDC underscore OV to S equals const based on TL level. This constant is found from a TL graph CHR pages 6. This will result in two equations with two unknowns which can be solved for the unknown dimensions of the Helmholtz resonator. It is important to note that flow velocities degrade the amount of transmission loss at resonance and tend to move the resonance location upwards. 3. In many situations, the long wavelength approximation is not valid and alternative methods must be examined. These are much more mathematically rigorous and require a complete understanding of acoustics involved. Although the mathematics involved are not shown, common filters used are given in the section that follows. Actual filter design. Edit vertical line. Edit source. As explained previously, there are two main types of filters used in practice, absorptive and reactive. The benefits and drawback of each will be briefly explained, along with their relative applications. See absorptive mufflers. Absorptive. Edit vertical line. Edit source. These are mufflers which incorporate sound-absorbing materials to transform acoustic energy into heat. Unlike reactive mufflers which use destructive interference to minimize radiated sound power, absorptive mufflers are typically straight-through pipes lined with multiple layers of absorptive materials to reduce radiated sound power. The most important property of absorptive mufflers is the attenuation constant. Higher attenuation constants lead to more energy dissipation and lower radiated sound power. Advantages of absorptive mufflers. 3. 1. High amount of absorption at higher frequencies. 2. Good for applications involving broadband constant across the spectrum and narrow band noise. 3. Reduced amount of back pressure compared to reactive mufflers. Disadvantages of absorptive mufflers. 3. 1. Poor performance at low frequencies. 2 Material can degrade under certain circumstances, high heat, etc. Examples: edit vertical line, edit source absorptive muffler. There are a number of applications for absorptive mufflers. The most well-known application is in race cars, where engine performance is desired. Absorptive mufflers don't create a large amount of back pressure as in reactive mufflers to attenuate the sound, which leads to higher muffler performance. It should be noted, however, that the radiated sound is much higher. Other applications include plenum chambers, large chambers lined with absorptive materials. See picture below, lined ducts, and ventilation systems. Reactive edit vertical line, edit source. Reactive mufflers use a number of complex passages or lumped elements to reduce the amount of acoustic energy transmitted. This is accomplished by a change in impedance at the intersections, which gives rise to reflected waves and effectively reduces the amount of transmitted acoustic energy. Since the amount of energy transmitted is minimized, the reflected energy back to the source is quite high. This can actually degrade the performance of engines and other sources. Opposite to absorptive mufflers, which dissipate the acoustic energy, reactive mufflers keep the energy contained within the system. See number sign the _reflector muffler reactive mufflers for more information. Advantages of reactive mufflers: 3. 1. High performance at low frequencies. To typically give high insertion loss, IL, for stationary tones. 3. Useful in harsh conditions. Disadvantages of reactive mufflers: 3. 1. Poor performance at high frequencies. 2. Not desirable characteristics for broadband noise. Examples: edit vertical line, edit source. Reflective muffler. Reactive mufflers are the most widely used mufflers in combustion engines. 1. Reactive mufflers are very efficient in low-frequency applications, especially since simple lumped element analysis can be applied. Other application areas include harsh environments, high-temperature flash-velocity engines, turbines, etc. Specific frequency attenuation using a Helmholtz-like device. A specific frequency can be toned to give total attenuation of radiated sound power, and the need for low radiated sound power car mufflers, air conditioners, etc. Performance edit vertical line, edit source. There are 3 main metrics used to describe the performance of mufflers: noise reduction, insertion loss, and transmission loss. Typically when designing a muffler, 1 or 2 of these metrics is given as a desired value. Noise reduction in our edit vertical line, edit source, defined as the difference between sound pressure levels on the source and receiver side. It is essentially the amount of sound power reduced between the location of the source and termination of the muffler system. It doesn't have to be the termination, but it is the most common location. 3. NR equals L page 1, L page 2 \display style NR equals \left L underscore P1 L underscore P2 \right. Or L page 1 \display style L underscore P1 and L page 2 \display style L underscore P2 is sound pressure levels at source and receiver respectively. Although NR is easy to measure, pressure typically varies at source side due to standing weights. 3. Insertion loss IL edit vertical line, edit source, defined as difference of sound pressure level at the receiver with and without sound attenuating barriers. This can be realized, in a car muffler, as the difference in radiated sound power with just the straight pipe to that with an expansion chamber located in the pipe. Since the expansion chamber will attenuate some of the radiate sound power, the pressure at the receiver with sound attenuating barriers will be less. Therefore, the higher insertion loss is desired. 3. IL equals LP, WIDHOUT, LP, WIDH \display style IL equals \left L underscore P without L underscore P with \right. Or LP, WIDHOUT \display style L underscore P without an LP, WIDH \display style L underscore P with our pressure levels at receiver without and with the muffler system respectively. Main problem with measuring IL is that the barrier or sound attenuating system needs to be removed without changing the source. 3. Transmission loss EL edit vertical line, edit source, defined as the difference between the sound power level of the incident wave to the muffler system and the transmitted sound power. For further information see transmission loss. 3. TL equals 10 liters of G1T \display style TL equals 10 log \left frac 1 \tau right with T equals ITII \display style \tau equals left frac I underscore TI underscore I \right. where IT \display style I_T and II \display style I_IR the transmitted and incident wave power respectively. From this expression, it is obvious the problem with measure TL is decomposing the sound field into incident and transmitted waves, which can be difficult to do for complex systems analytically. Examples: edit vertical line, edit source. 1 for plenum chamber, see figure below. TL equals 10 log S cos 2 PD2 plus 1. EASW \display style TL equals 10 log left edge left frac cos data to pi d circumflex accent 2 plus frac 1 alpha s underscore w right in decibels, where a display style alpha is average absorption coefficient. Plenum chamber transmission loss versus theta. 2 for an expansion, see figure below. NR equals 10 log 1 2 vertical line E, IKXS plus 1, S1 plus SCIKXS vertical line to 1 plus S2 display style and R equals 10 log left frac 1 2 left vertical line E circumflex accent x underscore S plus left frac 1 S1 plus S right E circumflex accent x underscore S right vertical line circumflex accent to left 1 plus S right circumflex accent to right. IL equals 10 log 1 plus S to 4 display style IL equals 10 log left frac left 1 plus S right circumflex accent to 4 right. TL equals 10 log 1 plus S to 4 S display style TL equals 10 log left frac left 1 plus S right circumflex accent to 4 S right, where S equals a 2 1 display style S equals left frac A underscore to A underscore 1 right. The expansion in infinite pipe and R, IL, and TL for expansion. 3 for a Helmholtz resonator, see figure below. TL equals 10 log 1 plus C to SLSB. C to V2 display style TL equals 10 log left 1 plus left frac left frac C to S right omega ls underscore B left frac C circumflex accent to omega V right circumflex accent to right in decibels. Helmholtz resonator TL for Helmholtz resonator. GDNRB. Links: edit vertical line, edit source. Muffler/silencer applications and descriptions of performance criteria. Exhaust silencers, engineering acoustics, Purdue University, MD 513. Sound propagation animations, exhaust muffler design project proposal and outline. References: edit vertical line, edit source. Kinsler, Lawrence E., Frame, Austin R., Cottons, Gallant B., Sanders, James V. Fundamentals of Acoustics. Wiley, P. 560. ISBN 978-047-1847892. Pierce, Gallant D. June 1989. Acoustics, An Introduction to Its Physical Principles and Applications. Acoustical Society of America. P. 678. ISBN 978-0883-1861-1. Weisstein, Eric W. Wave Equation One-Dimensional. Math World. Fundamentals of Acoustics. Kinsler et al., John Wiley and Sons, 2000. Acoustics, Pierce, Acoustical Society of America, 1989, MD 413. Noise Control, Dr. Mongo, Purdue University. Sound speed flow-induced oscillations of a Helmholtz resonator. Sound speed acoustics flow-induced oscillations of a Helmholtz resonator. Retrieved from https://wikibooks.org/w/index.php title = acoustics filter design and implementation and bolded = 3,547,097. Category: Book: Acoustics. This page was last edited on May 21, 2019, at 16:33. Text is available under the Creative Commons Attribution Share Alike license. Additional terms may apply. By using this site, you agree to the terms of use and privacy policy. Privacy policy about Wikibooks. Disclaimers. Code of conduct. Developers. Statistics. Cookie statement. Mobile view.